Okay, welcome everyone to, I guess, the first TCS Plus talk of 2024. Um, so TCS Plus is an online seminar to share ideas in theoretical computer science. And today we are very lucky to have Huan Lee from the University of Pennsylvania. He's going to tell us about parallel approximate max flow and near linear work and polylogarithmic depth. Just a few minor announcements, I guess, for people who are just joining. The talk is being recorded and we'll post it on our website. During the talk, I'll be monitoring the chat and I could relay some like clarification questions for Juan. But at the end of the talk, we're going to have just a non-recorded 15-minute session where we just get to discuss and ask Juan any questions that would warrant further discussion. So, okay, I guess with that said, let me hand over the floor to Juan. And yeah, please take it away.
All right. Thanks, Eric, for the nice introduction. Today, I'll talk about parallel algorithms for approximate max flows. This is a joint work with many wonderful collaborators, among whom I think my advisor Sanjeev is in the audience, and Nathan is also in the audience. Good. So the problem I'm going to talk about is the maximum flow problem, and its dual min cut actually has a long history dating all the way to the Cold War, where the US Air Force was very interested in a railway network between two major cities in the Europe. And in particular, according to a report declassified later, there were two main questions. First, how many resources can be transported between the two cities? And also how to disrupt this transportation between the cities with smallest budget possible. And these two questions are now well known as max flow and min cut problems, where the input is an n-vertex m-edge capacitated graph along with source S and sink T. And in the max flow problem, we want to route as much flow as possible from S to T without violating the capacity constraint. Whereas on the other hand, in the min cut problem, we want to separate S from T by cutting a smallest total capacity of the edges. And these are dual problems to each other, meaning their optimal values coincide. Therefore, from now on, we're going to only talk about how to compute a max flow in a graph. Good. Max flow is one of the most well-studied combinatorial questions in the literature. And there's a long history of works giving different methods, different algorithms to solve it. But here I want to mention three milestone algorithms in this line of work. So here I'm once again using M to denote number of vertices and M to be the number of edges. And I'm using this all-tailed notation as a convention to hide polylog vectors. The first milestone I wanted to mention is by Goldberg and Rao in 1998, where they use augmenting path-based techniques to get a runtime of m to the 1.5. And this works for directed graphs, and it computes exact max flow. And the second line of work, the second milestone I want to mention is a more recent breakthrough by Chen et al., which based on interior point method gives a runtime of m to the 1 plus small of 1. And this also works with directed and the exact max flow. And finally, the last milestone is by a joint effort of Sherman 13 and Peng 16, where they use gradient descent to get a runtime that is all-tailed of m over epsilon square. And here is for a more restricted regime where we have undirected graphs and 1 minus epsilon approximate flows. And by 1 minus epsilon approximate, I mean you still always get a feasible flow, except the flow value is only guaranteed to be at least 1 minus epsilon of the optimal. And these two runtimes here are known as almost linear time and near linear time. And in this talk, it's important to always distinguish between these two. Whenever we say almost linear time, it means the overhead is super logarithmic, something m to the small of 1. And also notice that up until now, all we have ever talked about is the runtime of an algorithm. That is the total execution time of an algorithm when you run it on a single processor with a single thread. But since we care about parallel algorithms in this talk, so what's going to be next is that we're going to introduce the PRAM model, which is now a very well-known model for parallel computation. Here, what we have is a collection of unlimited number of processors, and they have shared access to a common memory. And here we care about two quantities of an algorithm. First, the work, that is the total operations performed by all processors. This is the analog of the runtime in the sequential model. And also we care about depth, which is the maximum operations performed by any processor. And this, on the other hand, measures the adaptivity of an algorithm. So notice that here, processors can communicate with each other with essentially no overhead. So what that means is that the only issue when you want to turn a sequential algorithm to a PRAM algorithm is the data dependence, which in turn translates into the depth of the computation. And what this means exactly will be clear in the next few slides when we go over a small example of parallel computing. But what's the implication of this fact is that if you really want an efficient PRAM algorithm, you should really have an efficient sequential algorithm first. Good. With that takeaway, let's take a look at a very simple example for parallel computation. So we'll look at the following example where we want to compute the sum of an array of n elements. And the most immediate way to do this is to compute the prefix sums. So we'll start from 0 and sequentially add each element into the previously computed sum. The total runtime, or in the PRAM language, the total work is order of n. That's linear in the input side, which is great. But on the other hand, the depth is omega of n, which is bad because the depth is essentially the same as your work. So you're not exploiting the fact that you have a lot of processors to run these threads in parallel. And the depth is omega of n. The reason for that is because the computation of your prefix sum s of I depends on your computation of s of I minus 1. And this is what we referred to in the previous slide as data dependence. And also, it's what we call longest computational path in your program. But fortunately for this simple problem, we have a very clean resolution to give you a much better performance. So what you can do is as follows. We'll start from the entire array, and we're going to construct this binary tree. So we'll partition entire array into two arrays of equal length, and keep recursing on these two arrays to partition them further down until you get a singleton elements. And now with this balanced binary tree, what you can do is you can do this summation bottom up. You start from here, you add the two children to get the sum of the parent, and you keep going up till you get this entire sum. Now you get still linear work, but the depth will be order log n. So that's like an exponential speed up in terms of depth, which is great. Now let me say, what does it mean to get a great, very efficient PRAM algorithm for graph problems? So basically, the holy grail result for a graph algorithm in PRAM is to achieve a near linear work and polylog depth simultaneously. And the emphasis here is really to achieve these two simultaneously. Sometimes if you're willing to do more work, it's much easier to get a polylog depth. And turns out for some very classical graph computation problems in the literature, in the sequential algorithm literature, there are already known algorithms able to achieve these holy grail results. And these include graph connectivity, minimum spanning trees, shortest path, solving graph linear systems, and so on. I want to say none of these will seem obvious at first. For example, connectivity. If you think about doing breadth first search, depth first search, you will have a data dependence that is kind of linear in the diameter of your graph. But I guess more what's kind of surprising is that for the maximum flow problems, it's unknown whether such a result exists. And this is unknown even for undirected approximate max flow, this more restrictive setting. And that's what we're going to talk about in this talk. So before actually to getting into parallel max flow algorithms, what I want to do first is to explain why the sequential max flow algorithms are hard to parallelize. To understand why they are hard to parallelize is the key to at least in my opinion, is the key to understand the main challenges we're facing to get a very efficient max flow algorithms. So to this end, let me divide the existing max flow algorithms roughly into these two categories. Here we have combinatorial algorithms based on augmenting paths, push relabel, capacity scaling, and so on. And then we have continuous algorithms based on interior point method and gradient descent. And I just want to reiterate that our work will focus solely on the approximate undirected flow problems, although some of these algorithms work for the more general setting. Good. Now let's take a look at first categories. So combinatorial algorithms based on augmenting paths. Here's the idea, just to quickly do a recap. The idea is to repeatedly find augmenting paths from S to T in the residual graph, and then you update the residual graph accordingly. And this long life work starts from Ford Ferguson in 1956, and the most efficient one by Goldberg-Rao in 1998 gives you a runtime that is m to the 1.5. And these algorithms are hard to parallelize, is because you have to you have to find the augmenting paths for a polynomial number of times, and this augmenting paths findings, they are dependent on each other. You have to find the first path, you update your graph, then you find the next path, and so on. So these adaptive iterations are the source of the large depth, basically. Good. And then we have the second category, that is continuous algorithms based on interior point methods. Here, what they do is they borrow ideas from linear program, where we start from an initial feasible flow and gradually moving to the optimal maximum flow without ever violating capacity constraint. And this long life work is more, I guess it's more recent. It starts from Deutsch-Spellman in 2008. And as we have discussed most recently, breakthrough by Chen et al. Gives you almost linear runtime. However, they suffer from the same parallelization issue in that you have still a large number of adaptive iterations. You have to start from initial feasible flow and gradually move to the optimal maximum flow. Okay, so these two, I just want to reiterate, these two are for directed and exact maximum flows. And what we're going to talk about next is we're slightly switching gears to a more restrictive setting where we are focused on undirected and approximate flows. And this is also the setting our work focuses on. So I'm going to spend a little bit more time going over the notions, details, and techniques. So here, the idea is to use gradient descent to solve this maximum flow problem. And to run this gradient descent, what we need is what we call a good preconditioner of the maximum flow problem. And the preconditioner is also known as alpha congestion approximator. So what you should really think of this alpha congestion approximator is that it's really just it's a cut specifier, which means it preserves every ST cut of the original graph up to a multiplicative factor of alpha. But what's really so special, like why don't we just call it a cut specifier, is because it has this nice structure that is a tree. And that's what makes it, basically what makes it a linear operator. So you can plug it into gradient descent framework to compute gradient very efficiently. And because it's a tree, right? If you want to use a tree to approximate any arbitrary underlying graph, all you're gonna have to do is to use standard nodes. That is, nodes that are not in your original graph. Like here, every internal node of this tree is actually not a node in the original graph. So now, with this in mind, we're gonna have to slightly change the notion of cut approximation. So what we do is that if you look at any cut as a bar in the original graph, we're gonna look at all the cuts in this new graph that separate the two sides of the original cut. And we're going to take the minimum of all of those cuts. And we're gonna say this minimum is within the alpha factor of the original cut value. Good. And this alpha congestion approximator notion is very important because we in our work it's also one of our main contribution to give a parallel construction of such a congestion approximator. Good. So with this in mind, I'm now ready to tell you about what does the two milestone works Sherman and Peng did to really get efficient max flow algorithms. So first, Sherman 13 shows that if you give me an alpha congestion approximator, then I can give you 1 minus epsilon max flow in near linear time, with the overhead being polynomial of alpha and epsilon. And then subsequently, Peng 16 shows that you can actually construct a very high quality congestion approximator in near linear time, and therefore you can solve max flow in near linear time. And what's really good about this green descent framework is that it's unlike the previous ones, right? You have many polynomial adaptive, you have many adaptive iterations. And here is kind of more parallelization friendly. Number of iterations in particular is only a polynomial of alpha and epsilon, given that you have an alpha congestion approximator. And what this directly implies that if you have a polylog congestion approximator to start with, if you give me a polylog congestion approximator for free, what I can do is I can immediately give you a holy grail PRAM algorithm with near-linear work, polylog depths. So this reduction is like basically the core of computing efficient max flow. But however, the bad news for PRAM is that the construction of congestion approximator in Peng 16, if you just implement it directly, in the best scenario, it will only give you a depth that is super logarithmic. We will explain this in a little bit in a few slides. But the main question, especially the main question we want to understand in line of this literature is that can we efficiently get a polylog congestion approximator in near linear time and polylog depth? So yeah, that is the main question we want to understand here. And so basically now I'm ready to tell you what our results are. In this work, we answer this question in the affirmative. We show that there is a randomized PRAM algorithm to construct a polylogan distortion congestion approximator simultaneously in near-linear work and polylog depths. In other words, this is a holy grail PRAM algorithm for constructing a high-quality congestion approximator. And as an immediate corollary based on Sherman's framework, you immediately get this holy grail algorithm for approximate undirected maximum flows, right? And our result is the first to simultaneously achieve near-linear work and polylogarithmic depths for at least approximate maximum flow in the PRAM model. Good. So yeah, so that's pretty much about our results in the context of PRAM. Is there any question about our main results so far? Okay, so what's going next is that I'm going to introduce what are the implications of our results in the massively parallel computation model. It's yet another parallel computation model, but people would consider it to be more modern because it's motivated by Google's MapReduce parallel computation framework. So here, what's going on is that the edges of the graph are partitioned across machines with small memory each. And the computation will proceed in rounds, where in each round, the machine can send or receive limited information from other machines with the restriction that total size it sends or receives cannot exceed its local memory. And finally, after a synchronized round of communication, a designated machine, also known as the coordinator, will output the final answer. So for max flow, this coordinator will output the value of the max flow. And the goal here is to finish the computation in a small number of rounds and also with small memory per machine. Fortunately, to translate a PRAM algorithm to MPC, there's this very nice known reduction. So basically, what this reduction does is if you give me a PRAM algorithm, your work can translate directly to the total memory of all machines. and your depth translates to the number of synchronous rounds you need to compute. So, and this would immediately give us the following corollary, that is a near-linear total memory polylog around the MPC algorithm for approximate max flow. And this reduction is also powerful in the sense that it holds even when the machine memory is into the delta, as low as into the delta, where delta is some constant between 0 and 1. And this is known as the fully scalable MPC regime. So that is to say, in other words, our result is also the first to simultaneously achieve near-linear total memory and polylog rounds in this fully scalable MPC regime. Good. So that's about our results. So what follows is that for the rest of the talk, I will dive into more detail about the techniques in our results. So our algorithm it actually builds upon the framework in Peng 16, namely the sequential algorithm for near-linear time max flow. So what I'm going to do is I'm going to first talk about this sequential algorithm, how does it work, and then why it is hard to parallelize this sequential algorithm, the obstacles to parallelize it. And finally, I'm going to say what's our approach to overcome these obstacles to give you this polygonal PRAM algorithm. Okay. Does this plan sound good? Okay. So if this plan sounds good, so I will proceed into talking about the sequential algorithm of Peng 16. So Peng 16 algorithm, basically what it does, it gives you an efficient construction of a congestion approximator. Plugging which into Sherman's algorithm will then give you a max flow algorithm. And what it does to compute a good congestion approximator is to recursively call 3 subroutines in previous literature. And I do apologize, I will not be able to go into detail of each of these subroutines. But also, fortunately, on the positive side, all we need to know about these subroutines is what's their input, what's their output, and what are the guarantees. And those will be enough for us to understand how Peng 16 stitch them together to give you an efficient construction of congestion approximator. So first building block is Sherman 13, which we already talked about. What it does is takes congestion approximators and use that to compute approximate max flows. And then the second one is by Rika, Shah, and Aubig in 2014. What it does is kind of the opposite. It takes an kind of oracle or a known algorithm for computing approximate max flows, and it invokes that algorithm to give you congestion approximator of the input graph. And if you only look at these two, they're kind of circular. Their input and output are just switched, so it forms a deadlock or what you could call a chicken and egg situation. So, and the key to resolve this chicken and egg situation is to do ultra-stratification of the graph. This is a result by Spellman 1014 and Madrid 10. So what it does is it takes a dense graph, it gives you a sparser graph of smaller size while preserving the important properties we care about. And to me, this is kind of the key to make this whole composition of these building blocks work out in the end to give you the efficient construction. So what I'm going to do next is I'm going to take turns to introduce every one of these subroutines. So because I only introduced what are the input, what are the outputs. What I'm going to do next is to fill in more detail, like what are the parameters, what are the guarantees of these input and outputs. Good. So first one, Sherman's framework we already talked about. So we're given this congestion approximator, which I said you should just think of it as a cut stratifier, but it's a tree-structured cut stratifier that preserves every cut within a multiplicative factor of alpha. And then what Sherman 13 does, it uses gradient descent to compute a 1 minus epsilon max flow. And what's really important about these parameters here, like the runtime, the number of iterations, is that the overhead in both this time, the running time and number of iterations, is a polynomial of alpha and epsilon. So that's the main takeaway of Sherman's framework. Good. Now the second one, the Rika, Shah, Aubig 14 framework. It does the opposite. It takes a max flow algorithm and it produces congestion approximator. And so suppose we have this algorithm A for max flow, and then it will compute a congestion approximator of quality that is log to the fourth n. So just to fill in some parameter here. And then to guarantee that it will call this subroutine A on subgraphs whose total size is bounded by near linear in M. And by total size, I mean the total number of edges in these subgraphs, which you compute max flow on. Their number of edges, total number of edges is bounded by tilde of M. And finally, to solve this, like the accuracy to which we solve this max flow is 1 over log cube, so another parameter to fill in. And the main takeaway for this framework is that basically it needs high accuracy max flows on subgraphs of total size near linear in M. That's the main takeaway of this framework. Okay, now the third one, like the key to really make all this work is to do size reduction, is to take an input graph, output a sparser graph of smaller number of vertices and edges. So the number of vertices and edges will both be reduced by a kappa factor multiplicatively. And also, it will approximate every cut of the original graph within a kappa factor. And I'm putting quotation mark on this cut approximation because you can't really hope to approximate the original graph if you have fewer number of vertices. But what's really important is that this property, that is, if you have an alpha congestion approximator for the sparsified graph, what you can do is recover a slightly worse congestion approximator of the original graph with the guarantee being alpha times kappa. Basically, what's going on here is you are doing approximation composition. Like if you know x, y are within alpha, y and z are within beta, you would know x and z are within alpha times beta. I want to say that's always going on here. You're doing approximation composition. Good. So with all this in mind, we're now ready to take a look at how Peng 16 works. So for me, I think it's most helpful to first look at a high-level picture, like how, at least in which order Peng 16 is invoking these three building blocks. And only after that, it will be helpful to fill in the exact, to look at the exact algorithm detail and fill in what's the exact parameter we call each subroutine with. So to that end, let me first show you this high-level picture of Peng 16 algorithm. And the ultimate goal here is to compute a congestion approximator. So naturally, what we do is we run the Shah-Talvik 14 framework on the input graph G with the goal of computing a congestion approximator for it. And whenever in this framework, we need to solve approximate max flow on the subgraph, say G induced by vertex at S, what you do is to immediately do size reduction. That is a key step to make all this work, to make all this recursion work out without blowing up the size of your instance. You immediately do size reduction. You will call ultra sparsifier routine to sparsify this subgraph. And then what you do, you compute a congestion approximator of this sparsified graph. And you do that by, because you have the same goal, right, for computing congestion approximator, except with a smaller size instance. So what you do, you will recursively call the same routine in Shah-Talvik on this sparsified graph H. And this step is called a crude congestion approximator, because what's going on is you're computing congestion approximator of a approximation of the actual graph. So by the by the approximation composition we just discussed, this is going to give you a congestion approximator of worse quality. And that's why we call it a crude congestion approximator. And then we're going to plug back in this crude congestion approximator into Sherman's framework to compute high accuracy max flow. And this is what we call the boosting step, because you're taking crude approximation and you get a high accuracy max flow as your result. This is what we call the boosting step to avoid your blow up in the approximation ratio. And finally, you plug this back into your original Shah-Talvik framework, and you get what we call a good congestion approximator. So, okay, this is the high-level picture. Now, with this in mind, I think we're now ready to take a look at the more detailed algorithm with to look at the exact parameters of these subroutines. So So what we call good congestion approximator is the order log to the fourth n quality congestion approximator. This is basically the guarantee in this Rakesh-Taubig framework. And in order to do that, we will run this framework. And whenever we need to solve 1 minus max flow on a subgraph, what we do is we do size reduction with ultra specification of the subgraph. And the distortion here, and recall that this distortion not only decides the cut approximation quality, it also decides what's the size reduction you will get. So the larger the kappa, the worse the cut approximation, but the bigger size reduction you get. And we're going to fix kappa to be some polylog factors, and the specific polylog factor that we will need will be clear in the next slide when we analyze this runtime. And then we have the crude congestion approximator step, where we're going to recursively call the same routine on this specified graph H. And as we discussed by approximation competition, we know that if you really compute a log to the fourth n congestion approximator for H, you will get a worse congestion approximator for the actual subgraph. And the quality will be kappa times log to the fourth n. And finally, we plug this back into Sherman's framework to solve 1 minus max flow. And like the most important, most important quantity for analyzing this algorithm is that by the guarantee in Rakesh-Taubig 14, we know the total size of these subgraphs on which we call max flow. Their total size is bounded by O tilde of m. This is the most important point to the analysis of the algorithm. Very good. So basically, I claim now I can write the total runtime as the following recursive form. So when you run an instance of size m, I get a runtime of on an instance of size like kappa times smaller, except this O tilde notation. So we have size O tilde of m over kappa. And then I have the additional overhead of running Sherman's algorithm for the boosting step to compute max flows. So here I'm actually sweeping some tricks, some technical detail under the rug. That is, technically we're running this max flow on separate subgraphs whose total size is O tilde of m. But now I'm putting, after the size reduction, the total size will be m over kappa, and I'm putting the total size in the parentheses where actually it should be outside. And I can do this because we know the runtime is going to be at least linear. So actually it's going to be always super linear. So it's always, when you move them back in, it's always an upper bound. So now what we can do is we can set kappa to be some large enough polylog factor, basically large enough to overcome the polylog factors hidden in this O tilde notation, so that you actually get a true size reduction. So your size reduction will be always a polylog n compared to the original size. And then you could get a near linear runtime. So that's how Peng works to get the near linear runtime. Okay. So first, before I talk about the depths, is there any question about the Peng algorithm in the sequential model? All right. So the question we want to understand is that is this algorithm of polylog depths? This is actually kind of a tricky question, because for the longest time we actually thought this algorithm should give you a polylog depth. Because if you look at this recursion, what's going on is every time you reduce the size by polylog n, and then after log n over log n times, you get to constant size instance. But as I said, I'm sweeping some. So like the things I was sweeping under the rug is that this total size, it shouldn't be inside the parentheses, it should be outside. So what that means in particular is that if we take another look at this algorithm, right? We're running this max flow recursively, but we're computing congestion approximators recursively on the subgraph whose total size is bounded. But for this recursive clause, what's the dependence there? We haven't talked about, and it's not clear. And in particular, well, if they were really independent of each other, if you were really able to run this recursive calls completely in parallel, you would have gotten the polylog depth algorithm. But the problem is, are they really independent? And that's basically requires us to in turn take another look, at this truncated topic framework. Like we said, the guarantee is the total size bounded. But what about the dependency? And that's what we're going to do next. We're going to dive deeper into the truncated topic framework in the next few slides. All right. So how does it work? This will also help demystify how you get this tree congestion approximator with standard nodes, which is unclear, maybe not so intuitive just by looking at the definition. So what they do is that they actually compute a hierarchical decomposition tree. And what I mean by that is you start from the entire graph. You will run some subroutine to partition your entire graph, to partition the vertices of your entire graph into smaller partitions. And also by the guarantee in this paper, these partitions will also be roughly balanced. And what you are going to do is you're going to then, recurse on each vertex induced subgraph. Like here, if I do this partition, I will then recurse on the vertex induced subgraph induced by the vertices 1, 7, 8. I will run the same partition to do partition further down until we get singleton nodes. And then what's the congestion approximator? The structure will basically be the same hierarchical decomposition tree of the vertices you get here. So basically the leaves are true vertices in the original graph. And any internal nodes corresponding to bigger partitions are what we call standard nodes in this congestion approximator. And how, and also I want to say, because these partitions are balanced, so you will get a tree of order log depth. Okay, that's also important. And then how do they get these partitions? They get these partitions by running the very powerful cut matching game framework. They will run that framework to find the bottleneck edges to cut and then recurse on each side of the cut. And just an aside, this cut matching game is a very powerful computational framework for solving cut problems like sparse cuts, expander decomposition, and so on. But for the purpose of this talk, we will not go into the detail of that cut matching game. But we do need to know what are some steps in the cut matching game that could affect the depth of our algorithm. So let's take a look at that. The first thing in cut matching game that are of interest to PRAM algorithms is that we need to run 1 minus epsilon max flow on this vertex induced subgraph. So like here, again, if we look at this partition, what's the next the step we do to partition this further down is to run max flow of this vertex induced subgraph. And this in turn requires congestion approximator for this vertex induced subgraph. So that's where the recursion happens in the Peng framework. And the second thing we need in the cut matching game is to do flow decomposition. We did, given the ST flow, we did additionally to decompose the flow into ST paths. And this is strictly more information than a given flow, right? Because given a flow, what you don't know is how much flow are routed, for example, from this vertex to this vertex. But if you have the flow decomposition paths, you can look at how much paths, like how many paths, or what's the total capacity of the path that route flow from here to here. And this kind of subtask is known how to do in near linear time in sequential model by using data structures like dynamic trees. But the problem, once again, is that you need polynomial adaptivity, because what they do is they first find a path and they update your graph and use your data structure to efficiently maintain the state of your graph in order to efficiently find another path. And this inherently have this polynomial adaptivity. And also in PRAM, there's basically no known result whether you can do it very efficiently in polylog depth or not. So just to summarize, in this hierarchical topic framework, the sources of adaptivity come from two parts. The first part is you have this order login adaptivity because of the top-down nature of the decomposition tree. So what I mean by that is you can look at this decomposition tree. You have to start from here, so you compute the max flow here to do the max cut matching game. Only after that do you know the partitions, do you know these smaller partitions. So only after that can you recurse on these smaller partitions. So like we have this adaptivity from top-down nature. So this gives you order log and adaptivity because you have a log and adapt tree. And then, as we discussed, you also have the adaptivity of decomposing an ST flow into ST path. So with this in mind, we can first take a look at how the depths will look like. Right? Why doesn't it work out immediately? Because now the depths will have this recursive form where we have flow decomposition depths. The depth to run Sherman's algorithm, with this we know is polylog. Is going to be polynomial of kappa. Good, and then you have this summation of depths when you run your algorithm on geometrically smaller instances. And this is where the log and adaptivity comes in. This is why you have this summation of depth of geometrically smaller instances. Just to rearrange it, the flow decomposition depths we don't know. And actually the second second collection of terms we get here would appear to be more problematic in the sense that first, it's very hard in the sense that it's very hard to balance these two things. So to get really a polylog depth, you will gonna have to set kappa to be polylog n. And once you do that, then I claim you will get a super logarithmic depth from this summation of the smaller and smaller instances. And why that is the case, I will to understand why that is the case. Let's actually demonstrate this summation. Let's demonstrate this recursive form pictorially. So I'm just drawing the same recursive form in a recurrence tree, right? Start from the entire graph. You have to have this log and dependent recursive calls. And then for each call, you will further down have these smaller and smaller sizes and these small and also the log n dependent recursive calls of the smaller sizes. So what's going on here is first, the first thing to notice is the number of branches of this tree. The number of branches is log n. And also the tree, well, every level you reduce the size by kappa, right? And the tree depth is going to be log base kappa of n, which is log n over log n when you set kappa to be polylog n. And also, as we said, you're going to have to set a kappa to be polylog n in order to get the polylog depth. And what this means in particular is that your depth is bad in the sense that even if you have two dependent recursive calls, like imagine, like in the hierarchical topic framework, like this decomposition tree only have depth 3, for example. You only have two recursive dependent calls. Even that is the case, you're already in trouble, let alone you have actually log n branches here. So even if you have two dependent recursive calls, you have a branching factor of 2. Total depth you get will be branching factor to the power of your of the depth of the tree, right? So 2 to the log n over log n. That is like n to the 1 over log n, which is m to the small of 1, which is super logarithmic. That is bad, right? So that is the key problem with the Peng 16 framework. You're never gonna hope to get a total log depth if you do it this way. And our main technical contribution is basically to address these two sources of adaptivity. So our first technical contribution is to show that there is a PRAM flow of decomposition algorithm that simultaneously achieves near-linear work and polylog depth. In other words, there's a polygram or PRAM algorithm for the flow of decomposition problem. And this improves upon the polynomial depth of dynamic tree-based algorithms. And our second technical contribution is to give a new variant of the hierarchical topic framework, where we only ever need one recursive congestion approximator computation. As we have just seen, even two dependent recursive computation will get you in trouble. So we give a new variant that is that requires only one recursive computation. And this in turn requires opening up the black box analysis in Raki, Shah, aubig, and essentially giving a new proof for the new variant we provide. And these two together will now finally get you to this simple recurrence form where you have one flow decomposition, which is known as polylog here, and polykappa of Sherman, and then one single recursive call. And now the recurrence tree will look like just a single path, no branching factor at all. And you get the total depth of polylog as desired. All right. So I think this finishes discussion of our main technical contributions. So before I proceed to the next few slides, is there any question about these contributions or any obstacles there are?
So sorry, Juan, can you say just it's probably something that I was confused by.
Mhm.
You're saying that this poly K is coming from Sherman's framework?
Yes.
So that's you always add the poly K? Would it not? Why is it intuitively, why would you not multiply the depth if you're doing, let's say, poly K iterations of Sherman's framework?
So because so basically every iteration you will use the same congestion approximator. So once you have computed congestion approximator, you can just plug it in to run it for every iteration, reusing it for every iteration. So that's why it's a addition.
I see. So it's
Yeah,
okay.
yeah. Okay, so so in the remaining slides, I guess I'm gonna at least at a high level talk about what do we change, to talk about our contribution to talk about what we changed in the Rakeshri topic framework to get this only one recursive computation. So to really get only one single recursive call, basically what we're going to have to do is to reuse the congestion approximator in this hierarchical decomposition. Because of the top-down nature, right? Like you only, and also we only have one, we only have budget for one recursive call. And we're going to have to first, for the entire graph, you compute congestion approximator. And then after that, you get the smaller partitions. And now you're going to have to play a kind of matching game on these smaller graphs. But we can't afford computing congestion approximator for this again. So what that means, we're going to have to reuse congestion approximator of the bigger graph to use them as congestion approximator of the smaller graphs. But this is unfortunately unrealistic because I guess the one line reason is that the multiplicative approximation is not preserved under deletion. Because how you get from entire graph to subgraphs, right? You delete edges and vertices. And deletion does not preserve multiplicative approximation. Like this simple example, 99 approximates 100, but when you subtract, like 0, 1 are just mess up your approximation. And what is missing in the graph world is that the structure could be very different. Like I always like this example to demonstrate cut approximation. So you have a complete graph, and you have this so this is known as the Peterson graph, which is sparser graph. But notice that the edges are thicker, meaning they have high weight. That's what you need to approximate the dense graph with a sparse graph. But if you restrict to these three vertices, right, the induced subgraph here is a triangle, whereas on the right hand side you get singleton nodes. So you can possibly hope them to be approximation of each other. So what's the way around that is observation I'm going to show you in the next slide. So what if we, instead of deleting the other edges and the vertices, what if we do contraction? What if we contract every vertex outside of the vertices we're interested in? So now you will have the following picture. So now this triangle will be like, if you look at the vertices outside of these three vertices, you contract them into a single supernode, which is this gigantic node I'm drawing here. And you connect this node with every other node with these thick edges. Once again, they're thick because you have lots of parallel edges, right? After you contract them, um, like you have many edges going from other vertices to each one of these vertices we're interested in. So you have this structure of a thick star plus this triangle. And on the right-hand side, you also have the same star that is of the thick edges, but now you are like this triangle is absent, but that's fine because like these edges are not the dominant part. These thicker edges are always the dominant part of your cuts. So now you are able to get a good cut approximation multiplicatively. And this is the crucial observation we need to fix the issue we just saw in the recursive topic framework. So the changes we made is the following. So we will only ever run maxflow on contracted subgraphs by contracting the vertices outside of S, which is the current interesting vertices. And for example, if we want to look at the if we're interested in vertices 1, 2, 3, 4, 5, we will not look at the vertex-induced subgraph. We will only ever look at the contracted subgraph with other vertices contracted to a single supernode. And then we're going to run cut matching game on this contracted subgraph. And what that will give you is basically the balanced partition of this contracted subgraph. But for this hierarchical decomposition tree, right, what we want is actually a balanced partition of these interesting vertices. So what do? We just take out this supernode from whatever partition you get. Then I get a true partition of these vertices. And because your partition is balanced, so it will not ever be the case that the supernode is it is alone in a single partition. This will never be the case because of the balance of the partition. And also there's a technical detail which I'm glossing over. That is, we have to avoid the overusing of these boundary edges connecting to supernode with other vertices. Because if you look at this hierarchical decomposition tree, yeah, I guess if you look at this hierarchical decomposition tree, if you contract for every partition, you contract the thing outside. These boundary edges, they will appear in order log n of these contracted subgraphs. So to avoid overusing them, we need to lower the capacity of these boundary edges by some polylog n factor. And this will change your graph, but since it's multiplicative approximation, you can still use approximation composition to say, well, it's whatever congestion approximator I get, it's still congestion approximator, just worse by polylog n factor. So still, just by plugging into Sherman's framework, you get a max flow with just polylog overhead. And as Eric noticed, this Sherman's overhead is in addition, not multiplication. So we're still in good shape to get a polylog depth. All right. So, and what that means, well, what that means in this congestion approximator is that, okay, so here is an example. We have this entire graph, and we have computed its congestion approximator. And now we have we want congestion approximator for this contracted graph. And we want to we want to achieve that by reusing the congestion approximator here without any additional recursive calls, right? So what we do is we take this full congestion approximator and do the exact same contraction. So here you contract 6, 7, 8. I'm gonna contract the exact same verses here. And this will change the structure, of course, because like this is no longer a tree. But question, does this still work in Sherman's framework to compute gradients? Because we said this nice tree structure allows us to compute gradient. So it turns out we still can. It requires some few more tricks, but basically the high level intuition is simple. It's just because it's close enough to a tree. Okay. Now with this in mind, we have the new recursive algorithm to compute congestion approximator. Because notice that this is no longer log to the 4th end, it's log to the 9th end. It's worse because, as we said, to avoid overusing the boundary edges, we have lowered their capacity by some polylog n, and that eventually worsened our approximation. And we have the same size reduction, crude congestion approximator, and boosting step. But point is we only have one single recursive call. So basically what we do, we always do size reduction first. And after that, we're going to compute congestion approximator for the entire graph and reuse this congestion approximator for each contracted subgraph without ever recursing on them again. And that gives you this nice single path depth recurrence tree, which gives you the polylog depths at the end. All right. So just to conclude, in this talk, we have obtained the first approximate undirected max flow algorithms in PRAM, but simultaneously achieve nonlinear work and polylog depths. And also, we have said it has nice implications to the more modern MPC model. And I guess the first immediate question for our future direction for our work is can we improve the log factors in the depth? And I believe right now it's something around 60. And maybe another, I guess the most interesting question along this line of work is that can we get exact directed max flow in polylog depths and close to linear work? And finally, I guess another question worth mentioning is that could we apply similar techniques to apply to other models like the distributed computation model, congest, and so on? Yeah, that should finish my talk, and thanks everyone.
Okay, so thanks, Juan, for the talk. I guess, as promised, we can take us off the recording and we can ask any questions to Juan, have further discussion on the talk.